Welcome to my classroom. In this video, I will demonstrate some geometric problems which are difficult to be solved directly. Yet, by a suitable rotation, the problems can be transformed to a version which can be solved fast and easy. So the video is for students who want to learn more powerful techniques for solving geometric problems. Here is the first problem. ABCD is a square where the length of the side is not given. P is a point inside the square such that the distance from the vertices A, B, and C are 1, 2, and 3 respectively. We are asked to find angle APB. In this problem, we are only given 3 lengths which are the sides of 3 triangles ABP, BCP, and ACP. For these 3 triangles, we have 3 unknowns: the length x, the angles alpha and beta. Theoretically, we can apply cosine formula to set up 3 equations for these 3 unknowns. By solving the equations, we can find the answer alpha. But before you try, you can imagine the workload. Very complicated, right? You may try this later on your own. Here, I suggest another approach, which make good use of the condition of a square and try to connect the 3 given lengths in a triangle so that it can be solved easily. The way to do this is by rotation. Rotate triangle ABP about B clockwise by 90 degrees so that A coincides with C and P goes to P prime. Since triangle BPP prime is an isosceles right angle triangle, we have angle BP prime P equals to 45 degrees and PP prime is 2√2. Now, consider triangle CPP prime. 3 is the longest side, whose square is equal to the sum of the squares of the other 2 sides. By the converse of Pythagoras theorem, angle PP prime C is 90 degrees. Therefore, angle BP prime C is 45 degrees plus 90 degrees equals to 135 degrees, which is equivalent to the required angle APB. The answer is obtained. This is a problem similar to problem 1. This time, we are given an equilateral triangle ABC. P is a point inside the triangle. The distances from P to the 3 vertices are given, which are 3, 4, and 5. We are asked to find the area of triangle ABC. See if you can apply the techniques learned from problem 1 to solve this. Pause and try. Here is the solution. Rotate triangle ABP above B clockwise by 60 degrees to triangle CBP1. That is, triangle ABP is congruent to triangle CBP1. Triangle PBP1 is equilateral, and the area is 1/2 times 4 square times sine 60 degrees, that is √3/2. Triangle PCP1 is a right angle triangle with sides 3, 4, and 5, so the area is 1/2 times 3 times 4. We can do the same to the other 2 triangles, that is, rotate triangle BCP about C clockwise by 60 degrees to triangle ACP2, and rotate triangle CAP about A clockwise 60 degrees to triangle BAP3. Similarly, we have the sum of the areas equals to this. 50 with 3 over 4 plus 18. By rotation, we consider the congruent triangles with the equal areas, and therefore the above sum is a double of the answer. In other words, the area of triangle ABC is 25 with 3 over 4 plus 9. In the previous two problems, we considered the square and equilateral triangle. In fact, the condition of all sides equal is not necessary. Let us take a look at problem 3. Here is a quadrilateral with 3 lengths, 3, 4, 5, 2 sides equal, and an angle of 60 degrees as shown. Find the area of the quadrilateral. Pause and think about this on your own first. As there are 2 sides equal, rotate the triangle so that the 2 equal sides are coincide. That is, rotate triangle ABC about C clockwise by 60 degrees to triangle A'DC. Here, triangle ACA' is equilateral, and the area is 25 with 3 over 4. Triangle ADA' is right-angled, and the area is 6. Refer to the figure. We see that the area of the quadrilateral is the difference of the areas of the triangles. That is, 25 with 3 over 4 minus 6. Now, the problem looks like problem 1, a square with 3 given lengths. This time, the lengths are 3, 5, and 7. Find the area of the square instead of an angle in problem 1. Pause and try. To find the area of the square, it is equivalent to find the length of a side. Make use of rotation. Put 3 given lengths together to form a triangle for further calculation. So, rotate triangle ABP about B clockwise by 90 degrees to triangle CP'B. Thus, we have PP' equals to 5 with 2 and angle BP'P equals to 45 degrees. Consider triangle PCP', which is defined by SSS. Angle CP'P can be obtained by cosine formula. We have cosine theta equals to 1 over 3 with 2. Consider triangle BP'C, which is defined by SAS. BC can also be obtained by cosine formula. We have BC squared equals 34 minus 30 times cosine theta plus 45 degrees. Here, cosine theta plus 45 degrees can be expanded by compound angle formula. Simplify, we have 29 plus 5 with 17, which gives the answer, the area of the square ABCD. Here is a classical problem. Given a triangle ABC, an arbitrary triangle, P is a point inside the triangle. Find the location of P such that the sum of distances from P to the 3 vertices is minimum, and hence find angle APB. Would you like to try on your own first? Pause then. Unlike the previous problems, there are no equal sides or angles like 90 degrees or 60 degrees in this problem. Still, the technique of rotation can be applied. Rotate triangle APC about 8 anti-clockwise by 60 degrees to triangle AP'C'. Then, PC equals to P prime C prime for congruent triangles by rotation, and AP equals to P prime for triangle AP P prime is equilateral. In other words, PA plus PB plus PC equals to BP plus PP prime plus P prime C prime. For minimum sum, B, P, P prime and C prime are collinear. That is, P is somewhere on the line segment BC prime. To identify the location of P, we repeat the process by rotate triangle BPC about B clockwise by 60 degrees to triangle BP double prime C double prime. With the same argument, P lies on the line segment AC double prime. Therefore, P is the intersection of the two line segments BC prime and AC double prime. The location of P is identified. Now, let me redo the process of finding P. Rotate AC about A with 60 degrees to AC prime. Join BC prime. Rotate BC about B with 60 degrees to BC double prime. Join AC double prime. P is the intersection point. To find angle APB, remember triangle AP prime C prime is obtained by rotation of 60 degrees. Thus, triangle APP prime is equilateral. That is, angle APP prime is 60 degrees. Therefore, angle APB equals 120 degrees, adjacent angles on straight line. In fact, not just angle APB is 120 degrees. With the same idea, angle BPC and angle APC are both equals to 120 degrees. This point P is called the Fermat point, giving the minimum total distances from the three vertices of a triangle. In problem 5, I consider a triangle with the greatest interior angle less than 120 degrees. How about triangles with the obtuse angle equal to or greater than 120 degrees? Can you find the point within a triangle, that is, inside or on the boundary, in these two cases, such that it gives the minimum total distance from the three vertices of the triangle? In other words, find the Fermat point of these two cases. Try and enjoy.